Hello everyone, and thanks for watching Edupedia World Videos. In this video, we'll study a new property of many functions which is called continuity. So we've seen many functions already. We've seen the trigonometric functions, exponential functions, the inverse trigonometric functions. Some of these functions are what we call continuous, and others are obviously not continuous or discontinuous. Now there is a proper definition for the word continuous in terms of mathematics, but for most purposes it ends up being the same definition as it is for the English word continuous. So what you would generally mean by saying a function is continuous, that is what the official definition of continuous is, even though we'll give the definition in a minute. Let's start with a simple example first. Let's say we have a function fx which can take one of two values. Fx can either be 1 or 2. Fx is 1 if x is less than 0, and fx is 2 if x is greater than 0. And we need to define a value for x is equal to 0 as well. Let's say that for that also x is equal to 2. So fx is 2 when x is greater than equal to 0. How would the graph of this function look like? This is y, this is x. For x less than 0, fx is always 1, right? Let's say this is y is equal to 1, this is y is equal to 2. So this is the function, this is the function for x less than 0. And for x greater than 0 and equal to 0, fx has the value 2. So the graph for x greater than 0 or for the positive x-axis would look something like this. And you have fx is 2 when x is equal to 0 as well, and we represent it in such a way. We'll put in a hollow point here and we'll put in a solid point here. This just means that at x is equal to 0, the value is what we would have at the solid point or 2. So this is the graph for the function y is equal to f of x, which is 1 if x is less than 0, 2 if x is greater than or equal to 0. We can easily see from the definition of the English word that this function does not seem to be continuous. It has one line here and then it has another line here, where the point 0 is included in this line. This is clearly not continuous. A function like this, on the other hand, would have been continuous. Right. So the definition of continuous, the official definition is, if we assume that fx is defined in a domain, and let's say C is a point in that domain, this is just a way of saying that fx is defined at C. Then f of x is continuous at C at x is equal to C if the limit of the function as x approaches C is the same as the value of f at C. Right. Now you've already seen limits before in 11th class, and the limit of a function includes two things: the left hand side limit and the right hand limit. This is something you studied before. So the left hand limit means that x approaches C from the left. Another way to write that is limit x goes to C minus, which means that if this is the point C, let's say, then x can approach C from this side or this side. If it is approaching from the left side, we call it the left hand limit and we write it as x approaches C minus, or C from the side which is less than C. F of x is equal to f of C. And the right hand limit states that limit x goes to C plus f of x is equal to f of C. Right, so this is stuff which you already knew. For the limit of a function to exist at a particular point, the left hand limit and the right hand limit both need to exist and both need to have the same value f of c. Then the function is called continuous at the point c. Right. Another way of saying this, it's not a definition but it's an observation, that is that f is continuous at a point if we can draw its graph at that point without lifting the pen from the paper. Right. So if a function at a point C or near a point C, if the function goes like this, then you can obviously draw the function around C without lifting the pen from the paper. But if this is the point C and the function goes like this, then to draw the value of the function at C, you cannot draw it without lifting the pen from the paper. You draw this line, then you lift the pen from the paper, you put it back on the paper, and you draw this line. So that's a sort of informal observation for continuity of a function. Right. Also, if f is not continuous at x is equal to c, then f is called naturally discontinuous. Right. So fx can be continuous at a particular point in its domain if the left hand and the right hand limits of f are the same, that is f of c. Right. Let's go back to the first function we saw and see how that is discontinuous from this official definition of continuity as well. So the function we had was fx is equal to 1 for x less than 0 and it is 2 for x greater than or equal to 0. We saw the graph of this function as well. This was the graph of the function, where this is the darker point showing that this is the value at x is equal to 0. So let's look at the left hand and the right hand limits of this function. What is the left hand limit? That is limit x approaches 0 minus f of x. So this is the point x is equal to 0. As we approach it from the left, from this direction, we see that the limit is the value 1. Right. In fact, if x is less than 0, it doesn't matter how close it is to 0. If x is less than 0, fx has the value 1. So we can easily see this is equal to f of 0 minus, actually that's not a proper way to write it, I'll omit that. So this is equal to simply 1. Similarly, if we write limit x goes to 0 plus f of x, that means x approaches 0 from the right. It is a very small positive quantity. So no matter how small it is, as long as x is greater than 0, the value of fx is 2. So we know this is 2. And herein we see the difference. The left hand limit of x and the left hand limit of fx and the right hand limit of fx have different values at x is equal to 0. Therefore we can say the limit of the function at x is equal to 0 does not exist, which means f of x is discontinuous at x is equal to 0. It is not continuous at x is equal to 0. Right. What about another point? Let's say we take two other points. Let's say we take x is equal to 5 and x is equal to minus 2. So what about x is equal to 5? Limit x goes to 5 minus f of x is the value of fx when x approaches 5 from the left side. But it doesn't matter where it approaches from, as long as x is greater than 0, it is 2. And if x is just smaller than 5, then obviously it is positive still. So this is equal to 2 what is limit x approaches 5 plus f of x? That means it approaches 5 from the right side, but again we can see the value of fx is 2. Similarly, we can look at minus 2 and limit x goes to minus 2, minus, which means minus 2 from the left, fx, but if x is negative, fx is 1. Fx is 1 and limit x goes to minus 2 plus fx is also 1. So even though at x is equal to 0, the limit does not exist because the left hand and right hand limits are different. At x is equal to 5, the limit does exist because the left hand right hand limits are the same, they both have the value 2. And similarly, at x is equal to minus 2, the function is continuous. Another thing you can see is to draw the graph of this function near x is equal to minus 2, we don't need to lift the pen, we can just draw this line. Similarly, at x is equal to 5, we can just draw this line. But if we wanted to draw the graph of this function near x is equal to 0, we would have to lift the pen. We would draw this part, then we would lift the pen from the paper and have to draw this part. So from that informal definition also we can see that fx is discontinuous at x is equal to 0. However, it is continuous at x is equal to 2, at x is equal to minus 2 and x is equal to 5. In fact, you can prove for yourself that f of x is continuous everywhere except at x is equal to 0. So this is a function which is continuous everywhere except at x is equal to 0. At any other point you can just draw a straight line, but at x is equal to 0 you have to draw two lines, right? X is equal to 7, 9, 12, minus 15, all of them have fx being continuous. Right. Let's look at a few other examples related to functions we've already seen. Let's check the continuity of the function f of x is equal to 2x plus 3 at x is equal to 1. Let's check whether this function is continuous at this point. Now, whenever we are checking for the continuity of a function, the very first step is to see whether the function is defined at x is equal to 1. If fx is for some reason not defined at x is equal to 1, then it cannot be continuous at x is equal to 1 because the limits won't have any value which they need to be equal to. Let's say, just as a side case, if we had f of x is equal to 2x plus 3 by x minus 1. This function is not even defined at x is equal to 1 because fx goes to infinity. So there is no way this function can be continuous at x is equal to 1. However, this function is defined at x is equal to 1. Let's check for the continuity. What is limit x goes to 1 minus f of x? That is, again, you can directly see the proper way to do limits would be for x goes to 1 minus, you will take x is equal to 1 minus h, and the limit will be h goes to 0, and h always goes to 0 plus. That's why we took 1 minus h here, right? And if it was x1 plus, which we'll do in a minute, we'll take x to be 1 plus h. So limit of fx, this is the same as limit h goes to 0 plus 2 times 1 minus h plus 3, which is limit h goes to 0 plus 5 minus 2h, which is equal to 5 because h goes to 0, 2h goes to 0. Right. What about limit x goes to 1 plus? Also, we can see that f of x at x is equal to 1 is also 5. So we've proved here that limit x goes to 1 minus f of x is equal to f of 1. Right. Both are equal to 5. Limit x goes to 1 plus f of x means that I will just take x is equal to 1 plus h, and this will give me limit of h goes to 0 plus 2 times 1 plus h plus 3 is equal to the limit as h goes to 0 plus 5 plus 2h, which is 5, which is again f of 1. So the value of fx at x is equal to 1, which is 5, is the same as the left hand limit of fx at x is equal to 1, and it's also the same as the right hand limit of fx at x is equal to 1. So we can say that fx is continuous at x is equal to 1. Right. Now we could have actually seen this directly from the graph. The graph of 2x plus 3 will be something like this. And it's one straight line, so obviously it had to be continuous. Let's look at another function we've already seen. F of x is equal to mod of x, or the absolute value of x. This is defined as x if x is greater than 0 and minus x if x is less than 0. We can put equal to anywhere at x equal to 0, it's 0. Right. So first let's just, for the sake of it, try to do it by the graph, and then we'll actually do it properly. The graph of the function fx is equal to mod x. When x is greater than 0, fx is x. So we'll just have a straight line like this. When x is less than 0, fx is minus x. So we'll have a straight line like this. And we want to check for continuity at x is equal to 0. So we can see that we can actually draw the function near x is equal to 0 without lifting the pen and the paper. And so it should be continuous at x is equal to 0. Let's do it properly. F of 0, we know that fx is defined at x is equal to 0 and f of 0 is 0. What is limit x approaches 0 minus f of x? Now I'll just from now on do the limits directly. I won't put x is equal to 0 plus h or 1 plus h or something like that, because I know you've already studied that in the previous classes. So limit fx x goes to 0 minus is equal to limit x goes to 0 minus x, because for negative values of x, mod x is minus x. But again, as x goes to 0, this value is 0. Similarly, limit x goes to 0 plus f of x is equal to the limit x goes to 0 plus x, which is again 0. So mod x is indeed continuous at x is equal to 0. Let's look at another function, sine x, which is a function we've seen again and again. And let's try to look for the continuity at x is equal to pi by 2. Right. So what is limit x goes to pi by 2 minus f of x? Okay, before that, again I forgot. The first step is fx defined at x is equal to pi by 2. Yes, f of pi by 2 is equal to 1. Right. Limit fx as x goes to pi by 2 minus is equal to limit h goes to 0 plus, and we'll put x is equal to pi by 2 minus h. So as h goes to 0 plus, sine of pi by 2 minus h. But that can be written as limit h goes to 0 plus cos of h. And as h approaches 0, cos h approaches 1, so this is equal to 1. Limit x goes to pi by 2 plus f of x will simply be limit x goes to h goes to 0 plus, and we'll take x is equal to pi by 2 plus h now, sine of pi by 2 plus h, which gives me again cos h, not minus cos h, because in the second quadrant sine x is positive, so this term has to be positive, and this is again equal to 1, which is again f of pi by 2. They both are equal to f of pi by 2. Hence sine x is continuous at x is equal to pi by 2. In fact, we could have seen this directly from the graph. Near pi by 2 the graph is like this, so it certainly is continuous. Right. Let's look at one final example before moving on. Y is equal to e to the power x. The graph of this at x is equal to 0, e to the power x is 1, at x is equal to 1, it is e, and as x goes to infinity it's infinity, as x goes to minus infinity it goes to 0. So the graph is something like this. And you can see that if say at x is equal to 1, where this is e, the graph is continuous. Let's do that formally as well. We need this at x is equal to 1. So first of all, f of 1 is equal to e. What is limit x goes to 1 minus f of x? That will be limit h goes to 0 plus, we'll put 1 minus h, so e to the power 1 minus h, right, which is limit h goes to 0 plus e divided by e to the power h. As h goes to 0, e to the power h goes to 1, so this is equal to e, which is f of 1. So the left hand limit is equal to the value. So e to the power 1 plus h, which will be e times e to the power h. E to the power h again goes to 1, so is equal to e, which is f of 1. So e to the power x also is continuous at x is equal to 1. Okay. Up till now, we've only talked about continuity at a particular point. But generally, it's more useful to talk about the continuity of a function in a region. So let's say the region we are talking about is a comma b. The closed brackets denote that a and b are included. This means that x is greater than equal to a and is less than equal to b. Right. So let's say fx is a function which is defined in a region a comma b with closed brackets, which means x can be a or b or anything in between them. Now, a function is called continuous in the region. Remember, we only talked about continuity at a particular point till now. It is continuous in the region a comma b if it is continuous at every point in a comma b. So if it's continuous at every point within a region, then it's continuous within the region. When we saw the continuity for fx is equal to sine x, the graph between 0 and pi went like this. So we saw it's continuous at x is equal to pi by 2, but in fact it's actually continuous in the whole region 0 comma pi. In this whole region, sine x is continuous. There is one small intricacy, however. For every point except a and b, we need both the left hand and the right hand limits of a function, of the value of the function, to be equal to the value at the particular point. Say if we take a point between a and b, say c, then the left hand limit at c needs to be equal to the right hand limit at c, and both of them need to be equal to the value at c. I'll just write it down. Let's say c is a point between a and b. Then for f to be continuous at c, limit x goes to c minus f of x should be equal to limit x goes to c plus f of x, and they both need to be equal to f of c. If this is true, it is continuous at c, which is a point between a and b. At a and b, the situation becomes a little tricky. If the function is defined between a comma b, that means it is only defined for a less than equal to x less than equal to b, then x can never be less than a. It can be equal to a or greater than a, but never less than a. That means the left hand limit at x is equal to a is not even defined, because the function may not be defined at that point. So for continuity at a, all we need is the right hand limit needs to be equal to the value. So this is for any c between a and b. And for a and b, the condition for continuity will be limit x goes to a plus fx is equal to f of a. Limit x goes to a minus f of x does not exist because fx has the domain between a and b, or rather we are considering fx between a and b. Similarly for b, the left hand limit makes sense, but the right hand limit does not make sense because x can at most be b, it cannot be greater than b. So for b, limit x goes to b minus f of b should be equal to, f of x should be equal to f of b. If the first condition holds for all c between a and b, the second condition holds for a, and the third condition holds for b, then fx is continuous in the region a comma b. Just to look at it from the graph, let's say this is a point A, this is a point B, both are included, and the function is the function can't be like this, it cannot go back up. Let's say the function is something like this. So for any point in between A and B, it needs to be continuous. That means both left hand and right hand limits should exist. But for this point, the left hand limit doesn't really exist because we are only considering it between A and B. So only the right hand limit needs to be equal to A. What would the graph look like if the right hand limit was not equal to A? We would see something like this. This was A, this was B. The value at a particular point A would be this, but then the function would go like this. Then the right hand limit of A would be this value, but the value at A would be this value. So it would not be continuous. But here, the right hand limit at A needs to be equal to value at A, and the left hand limit at B needs to be equal to the value at B. Right. So these three things need to be true. The left hand limit of A, x goes to A minus f of x, and the right hand limit of B do not make sense. I would say they do not exist, but they may exist if the function actually exists, but we are only considering between A and B. So as long as we are considering between A and B, these two terms do not make sense, and these are the three results that need to be valid in order for the function to be continuous in a region A comma B. Let's look at some examples of functions and whether or not they are continuous in a region. Let's start with the function f of x is equal to 1 by x. Right? And let's see whether this is continuous or not at x is equal to 0. So limit x goes to 0 minus 1 by x will be, we'll just put x is equal to 0 minus h, or minus h minus 1 by h, which we can see now h is positive, and as h goes smaller, 1 by h grows larger. 1 by h in fact goes to infinity as h goes to 0. So this goes to, we can't write equal to, we say goes to minus infinity, which means the limit does not exist. Similarly, we don't need to check it really, but x goes to 0 plus 1 by x will be limit h goes to 0 plus 1 by h, which will go towards plus infinity. So again, it does not exist. So f of x equal to 1 by x is actually not continuous at x is equal to 0. We could have actually seen that directly. Fx is not defined at x is equal to 0, therefore there is no way it can be continuous at x is equal to 0. Let's look at another interesting function which you've already seen before, the greatest integer function. It is denoted by a square brackets around x, and this is the greatest integer which is less than or equal to x. So for example 2.17, greatest integer of x would be 2. It is the greatest integer that is smaller than x, smaller than or equal to x. For x is equal to 2, greatest integer would still be 2. So before looking at the actual limits, let's draw the graph of this function and see if we can determine anything from that. If x is 0, then greatest integer of x is 0. As x increases from 0, it becomes 0.1, 0.2, 0.3. Greatest integer of x is still 0. So it goes like this until x is equal to 1. Now, if x is just less than 1, let's say 0.99999, then the greatest integer of x will be 0. But the moment x becomes 1, the greatest integer of x is 1. That's why there is a solid dot here. Then we go till 2, and at 2 the greatest integer of x becomes 2. And it increases and then 3. This point towards the left is 2.99999. At that point, the greatest integer of x is 2, but at 3, the greatest integer of x is 3. And so this is how it goes. Then you'll have this. All of these are solid points because these are the values at 2, 3, and 4, not the less one. So we can see directly from the graph that the greatest integer function is discontinuous at all integer values and continuous everywhere else. But let's try to do it practically. So let's say we calculate it about n, which is an integer. N could be 2, 3, 5, 7, whatever. Then limit x goes to n minus greatest integer of x will be, so if n is, let's say, 3 or any integer, then just before that the greatest integer will be 1 less than that. So this will be n minus 1. But as limit x goes to n plus x, this is the first one was 6.99999 if x is 7, that would give me 6. The second one is 7.001 if x is 7, so this will give me 7, which gives me n. So even from here we can see that at all integer values of x, the greatest integer function is not continuous. Now there are many rules regarding continuous functions. If f of x and g of x are continuous in a region, then so are f plus g, because if limit x goes to a particular value f exists and the limit x goes to the particular value g exists, then their sum must also exist, right? F minus g is also continuous, f multiplied by g is also continuous, and f divided by g is continuous, except where there is an exception here, except at points where g is equal to 0. Because at those points f of g will not be defined. Everywhere else f by g will be continuous, and the first three will be continuous everywhere in that region if fx and gx are continuous in that region, right? So from that we can actually deduce the values of many other functions, deduce the continuity of many other functions. Let's look at sine x and cos x. I won't try to derive the continuity here, we just draw the graph. The graph of sine x goes like this. And the graph of this is sine x, which is 0 at x is equal to 0. This is the graph of cos x. And we can see just from the graph that sine x and cos x both are continuous everywhere. Right, because we can just create this curve to infinity without lifting the pen from the paper. So they are both continuous everywhere. What about sine x by cos x, which is tan x? Let's draw the graph for tan x. I assume you already know graphs for tan x and stuff. In fact, we've already seen graphs for inverse functions as well. So this is 0, this is pi by 2, pi, 3 pi by 2, minus pi by 2, minus pi, minus 3 pi by 2. At x is equal to 0, tan x is 0. As x approaches pi by 2, tan x approaches positive infinity. And as x approaches minus pi by 2, tan x approaches negative infinity. So between minus pi by 2 and pi by 2, this is how the graph looks. Now there are many other possible values as well. Between minus pi by 2 and pi, this is how the graph looks. Between minus 3 pi by 2 and minus pi by 2, this is how the graph looks. Right. So we can see that tan x is discontinuous at x is equal to pi by 2. This point, because the left hand limit is positive infinity, the right hand limit is negative infinity. Not only that, it is not even defined at pi by 2. 3 pi by 2 minus pi by 2 and so on. So these are the points where tan x is discontinuous. But we can see that directly from the previous rule that we've seen. If sin x and cos x are continuous everywhere, then sin x by cos x will be continuous everywhere except where the denominator is 0. So cos x is 0. And where is cos x 0? At x is equal to pi by 2, 3 pi by 2 minus pi by 2 and so on. Right. So this is how we can deduce results for continuity of tan x, cot x, cosec x and so on. Because we already know sin x and cos x are continuous everywhere. So any quotient of them, whether it's sin x by cos x, 1 by sin x, they all will be continuous everywhere except where the denominator is 0. This is not just true for sin x by cos x. All polynomials are continuous. Because they don't have anything in the denominator. And fx is equal to a constant is continuous, fx is equal to x is continuous, x square is continuous, x cube is continuous, so their sum will be continuous. Now if f of x is equal to p of x by q of x, where p and q are polynomials, then fx is called a rational function. And these are continuous everywhere because polynomials px and qx are continuous everywhere except where, you guessed it, q of x is equal to 0. And finally, there's one last result which we'll state without proof. We've already seen composite functions f of g of x is equal to f of g of x. Now if g is continuous at a point C and f is continuous at, now if g is C, the argument of f is g of C. So if g is continuous at C and f is continuous at g of C, then f o g of x is continuous at C. So for example, take sine of x cube. We know x cube is continuous everywhere. We know sine of something is continuous everywhere. So sine of x cube will be continuous everywhere. This completes continuity. In the next video, we'll study a similar concept called differentiability. Just like continuity says the limit must exist on both sides, differentiability says that the derivatives must exist on both sides. So we'll see that in the next video. Thank you.